We're going to talk about special right triangles. Special right triangles are triangles we use so frequently that we've memorized their dimensions and the scale factors that we use. The two special right triangles are a 30-60-90 triangle and a 45-45-90 triangle. We can use a scale factor to convert between these triangles and the triangles we're given in diagrams. And so I'm going to put an A next to the sides of the triangles that we're using, so that when we're trying to convert between our triangles, we can just use these sides and put an equal sign next to it. You'll see how it works. Here's an example of a triangle where I'm asked to find two sides, and I'm given that the longest side is 10. These are special right triangles, even though they're not drawn to scale, and we can say that this is 60 degrees on both triangles, so we know we can use our template. So I'm going to take 10, which is the longest side, and I'm going to put it equal to 2a. And this side I'm going to say is equal to a, and this is going to be equal to a square roots of 3. So now that I have that equation set, I can find out what a is. All I need to do is take this equation, 10 equals 2a, and divide by 2. So I have a equals 5. And then I can fill in the other parts of the triangle that I need to know. So this side is just a, and since this side is a square root of 3 and a is 5, I can say it's 5 square root of 3. In this example, the triangles are oriented differently, but we can still say that I've got one of the short sides of this isosceles triangle that's 45, 45, 90, which makes it one of our special right triangles. So if I have 6 and I want to know the other sides, I'm going to fill in the letters from my reference triangle and label my sides as AA and a square root of 2. And then I'm going to look at my side that I'm given. Since 6 equals a, that other side's also going to be 6. And this side's going to be 6 square root of 2. In this triangle, we're given the long side and that it is a special right triangle. The sides are isosceles, the legs are. So we can set up our equation just like we did before by bringing over the a square root of 2 from our reference triangle diagram and bringing over the a from the short sides. And now we're left with this equation here, 11 equals a square root of 2. To find the short sides, we're just going to divide by square root of 2. And these cancel. And you could write down that a equals 11 square root of 2, or 11 over square root of 2. It's not considered to leave a radical in the denominator is not considered proper. So we normally change this to a decimal or rationalize the denominator, but that's something we're going to do in a separate video. And for now, and on your homework, it's acceptable to leave denominators without rationalizing them. One last example. This time the 5 is on the side of the long leg where x squared root of 3 goes. And so we're going to copy our dimensions over x, 2x, and x squared root of 3. And we're going to take the side that has the x on it and the number that we're going to solve for. So if we say that 5 equals x squared root of 3, we can divide by square root of 3. We can get x equals 5 over square root of 3. This is a little bit ugly and it's not rationalized, but we're going to work with it for now. We'll rationalize square roots in a different lesson. And we'll say we've got 5 over square root of 3 here for x. And then for this side, we can say we've got 2 times 5 over square root of 3, which is 10 over square root of 3. And these are our answers to the other sides. It's not considered proper to have a radical in the denominator, so to get rid of it, we multiply by that same radical over itself. And so in this case, that would change it so that the denominator was a rational number. So we'd have 5 square root of 3 over 3. And if we wanted to rationalize the other answer, 10 over square root of 3, we'd multiply by square root of 3 over square root of 3. And we'd get 10 square root of 3 over 3. Sometimes we would still need to keep reducing if we could reduce something like 10 over 3, but in this case, that's as far as we can go.